Okay, hello everyone. In this episode we're going to be looking at hypothesis testing for a mean. So let's go through the process and then I'll go through a few examples. So there are a few things you need to do when you're doing a hypothesis test. Essentially what I've got here in these dot points is the procedure for what you have to go through. So hypothesis testing is sort of like a scientific investigation. You are given a claim or something you want to research, and from that you want to try and reach a conclusion about a hypothesis. So first off, a claim is made. Generally at this level we'll probably be looking at a claim about the mean of a sample, or a mean of a population, sorry. And this claim is generally represented by the null hypothesis, which involves no change. So say I wanted to claim that all bread that I make from my bread company will have a mean weight of 85 grams for a small bread roll or something like that. Well, the null hypothesis in that case, the claim I've made, is that the average weight of bread, or the mean weight of my bread roll, would be 85 grams. So the alternate hypothesis is that the actual claim that I've made, or the null hypothesis, is not indeed true, or there's not enough evidence to support that it's true. Insufficient evidence to support it's correct. Again, you can't disprove anything with this, because you're looking only to a certain significance level, but you can say there is not a lot of evidence to support said claim or said event. Because of course, as we know, the normal distribution stretches out forever, so really anything is possible. There are very unlikely values, which we can say would be very unlikely to be true, but again, when we're looking at the 0.05 significance level, we're looking at things that 95% of the time are going to be true. So when we say that the bread roll may not actually have that mean weight of around about 80 grams, as I said before, I'm technically saying that there isn't enough evidence to support it, because 95% of the actual probabilities, it doesn't lie within the 95% region. Okay, and the alternate hypothesis, as I said before, is that it's not going to be that weight. But what happens in a question that you'll be pitched is generally there's a sample that's taken, and you'll be given a sample size or a standard deviation, and from that it asks you to calculate the test statistic, which I'll go through in just a moment. But before that, in some questions it may specify to write a distribution of the test values that you were given, which I'll also go through. But the test statistic, it's again very much like the z-score. However, instead of a random variable x, we have the so-called sample mean that we get from the sample. Maybe the sample's trying to disprove the certain thing, it generally is the case. And we've got subtract mu, and mu, of course, is the population mean. But unlike just having population standard deviation sigma in the denominator there, we've got sigma over square root n, because we are working with sampling, and you may remember from my central limit theorem video that sigma over n is sort of, in most regards, the standard deviation of a sample. And lastly, after test statistic is used, which I'll go through in a moment, a p-value is calculated, and this p-value represents the significance. So how significant is it for a value to lie in a certain place? And once we've done that, a statement is generally made. We either support the null hypothesis, which is denoted, as you can see on the board there, by h and subscript 0, or little o, or alternatively we can support the alternate hypothesis, depending on what our results show us. So that's the process for hypothesis testing with a mean. I guess it probably won't mean a lot, and of course the pun's not intended there, but it won't mean a lot to you at the moment until you see a few examples. But essentially what we've got is we've got a claim, maybe a company's making some claim or something, and we take some samples and we see whether that claim could be possible, or whether there is enough evidence to support it. So again, very similar to what you do with scientific investigations, where you go in the lab, you have a hypothesis and you test the hypothesis, and then you see whether you got evidence to support it or evidence to say that it wasn't supported. Again, you can never prove or disprove anything, because there's still a very small probability that that the sample mean and the population mean in those questions may actually work. Okay, so in terms of hypothesis testing, what I'll start off with is a concept drawing, and this is of the normal distribution. And we're assuming that our data is normally distributed again for these questions with hypothesis testing on the mean. But in this case, let's say we've got the mean somewhere in the middle, and let's pretend that that's perfectly symmetrical even though it isn't. Essentially what we do at a 0.05 significance level, which means that we're going to be 95% likely to be correct, is we essentially say, well, okay, we're looking at where the value of x bar lies, and if x bar lies outside of a certain point, where there's 2.5% under the curve on this side and 2.5% under the curve on that side, then we know that's quite an extreme example, and that it's very unlikely that that's the population mean is actually going to link up. So let's say we had a value out here, we worked out x bar, and we got it out there, then we would say that the alternative hypothesis would be supported at the 0.05 significance level. And alternatively, as I drew up here before, if we had the sample mean lying in the middle here, without being in the 2.5% well below or above the mean, then we could say that, okay, there is sufficient evidence to say that that mu value there could quite possibly be the real population mean. So again, that 0.05 significance level comes from the fact that there's 95% of the values there, and we just exclude 2.5% each side as being the extreme value. So anything beyond that kind of point is where you start getting an extreme value for your sample mean. Again, it doesn't mean that this population mean, or the claimed mean, isn't correct. It just means that at a certain significant level, it is very unlikely. So now I'm going to go on to a few examples. Hopefully I cleared it up. Again, we're just thinking, we're looking at sample mean and where it fits relative to the actual claimed population mean to see whether the claimed population mean is correct. Okay. So hopefully you've noted down the process. So now what we want to do is work our way through the question. And the question says, a random variable x is normally distributed with a standard deviation of 4. And when they give standard deviation in all these questions, it's denoted by sigma, so hence it is population standard deviation. They will always give you population standard deviation, and from that you work out standard deviation of the sample. So in this case, sigma is equal to 4. It is claimed that the mean of x, which is denoted by mu because it's a population mean, equals 17. To test this claim, a random sample of size 50 was taken, and the sample mean, which is denoted by x bar, was claimed to be 16. Write down the hypotheses for the null hypothesis and the alternate hypothesis. So the null hypothesis is given by h subscript little 0, little naught there, and in this case the alternate hypothesis is also denoted by h little subscript a as little subscript. So what we do now is we say, well, okay, the null hypothesis is that there is no change, so hence the null hypothesis, or the claim made, is going to be that mu is 17. The alternate hypothesis is that mu is not going to be 17. And again, what we do is we look at the 0.05 significance level to see whether it's very possible or very likely or very unlikely for the mu to be 17 or for the mu not to be 17. So now we think about writing down the null distribution. So null distribution is the distribution that we have from our actual sample here. So null distribution, our variable is x bar, which we got from our samples, and we're looking at a normal distribution, so this is standard notation here, and the mu value that is claimed is 17. And also our standard deviation has to be sample standard deviation. So this is given by sigma, which is a population standard deviation, on square root n. And n is of course 50 because that's the size of our sample. And you may note that the sample standard deviation is squared there. That's because you may remember that the normal distribution is given in the form of mu sigma squared. In this case, it's sigma of a sample. And because it's sigma of a sample, as covered previously, it's going to be population standard deviation on square root sample size. So that's the distribution we're looking at. And that's generally step 2. So you've thought about what the actual null hypothesis is, what the claim is being made is, and you've looked at what the alternate hypothesis is. Now you actually calculate the test statistic. So in order to calculate the test statistic, we use, as I showed at the beginning, the z-score formula. However, we use the sampling adaptation, where we use sample standard deviation, which is given by sigma on square root n. You may also see this sample standard deviation denoted by s little x. There are many ways of denoting it. So now z equals, and what I'll do is I'll also show an example on the calculator after we've done it algebraically, but z equals x bar take mu on sigma over square root n. X bar is our sample mean. So, from the question we're able to put in the values and calculate where this lies on the distribution. Again, we're working out simply where the sample mean actually fits with the sample standard deviation subbed into the z-score. Will you remember what z-scores are? How many standard deviations is from the mean? That's essentially what we're doing here. How far is the sample mean from the claimed population mean? Because if they're very far apart, then it's looking unlikely for the actual population mean to be correct. Wouldn't you agree? So, x bar is 16. Take mu, which is 17. And that is all over sigma, which is 4, and square root sample size, which is 50. Again, you get all these values from the question. So now, we go ahead and calculate this. So we get our z-score. And 16 take 17 is of course going to be -1. So it's going to be -1, 4 over square root 50. So now we can use our calculator to work out what this value would be in terms of a z-score. So in order to do this, we turn our calculator on, we go alpha first, alpha y equals, and then go down to 2 to get a fraction bar. This is again on a TID4. Then you go -1, then you use the arrow to go down to the bottom, and you press alpha alpha stat y equals, and again you go down to 2, and then you have 4 over square root of 50, and you get -1.76. So we calculated the test statistic, which is good. But now the next question actually says to calculate the p-value. Now again, the p-value, if p is less than 0.05, then we actually reject the null hypothesis based on the evidence given. Because of course, that's quite unlikely to happen for the actual population mean to be what is claimed. So that's when we reject the null hypothesis. However, if p is greater than 0.05, then we reject the reject the alternative hypothesis, which means that we actually accept the null hypothesis and hence say it is the evidence supports that the population mean is close to or could actually be what was claimed. So in order to work out our p-value, we first need to conceptually understand what it is. So if we have a look here, we have some value lying out there for x bar, and we have some other value out there. And they both have a z-score. One has it of negative 1.76 and the other has it of 1.76. But from this, what we want to do is we want to work out the probability that's either at that end of the extreme or at that end of the extreme. And you may think, okay, I need to work out the probability for both using normal CDF, because normal CDF gives us a proportion under the curve. And, well, technically you are correct. However, what we can actually do is, because these areas are going to be the same, we can actually work out the area for 1. And then multiply it by 2, and then we get our p-value, which is essentially telling us how likely it is for that value, again, to what the significance level is in terms of p. So in order to do this, we go onto our calculator and we go to normal CDF. And what we do is we type in our lower limit of negative e to the power of 99 and our upper limit of negative 1.76, and we assume, again, that we standardize the distribution, so we have 0 and 1. And as a result, we go to second function distribute, normal CDF, type in these values to work out the p-value, the significance level. And as a result, we get the probability is 0.0369, and that's less than 0.05, which is the significance level we're looking at. However, in this case, again, we've got to times it by 2, because it could be at the other end of the extreme. And when we do that, we are able to work out, we go second function answer times 2, and we are able to work out that's actually 0.078 as the significance level. 0.078. And it's because of that we don't actually reject the null hypothesis, because that p-value is greater than 0.05. So as p is greater than 0.05, the evidence supports the null hypothesis, which is, again, denoted by that. And that would be the statement we'd make. And we could say that the null hypothesis was, again, that mu equals 0. In fact, mu equals, 17. But you could add to that and you could say, at the 0.05 significance level. And again, it tells us that we've actually went through the process and we've checked to see whether the sample mean could actually be in some correlation to the population mean, or whether they were too different. So again, because we got that certain level of similarity, or that certain level of the possibility of the population mean being correct, we can actually make that final statement. So hopefully you've seen how to go through the process. That was a very sort of guided process there, because it wasn't a contextual question. But what it actually asks us for next is to go into a more contextual question. And the contextual question is based around the concept of peaches and preservatives that are put into peaches. So again, we're going to test a claim made by the company who produces these peach cans, and we're going to work out whether the population mean that they claim is correct, the population mean of the preservatives that are squirted out of the machine. So again, there are quite a few real-world applications of hypothesis testing. So with this question, we are told that peaches are being canned and that 250 milligrams of preservatives are supposed to be added by a dispensing device. It is known that the standard deviation of the preservative added is 7.3 milligrams. To check the machine, the quality controller obtains 60 random samples of dispensed preservative and finds that the mean preservative added was 242.6 milligrams. At a 5% level, is there sufficient evidence that the machine is not dispensing a mean of 250 milligrams? So for this example, we're going to write down and identify the key factors, and then I'm going to show you how to use your calculator to solve this, and then we're also going to look at how to do it by hand as well. So the key information: a machine is meant to dispense a mean of 250 milligrams. However, it is known that from the sample size, the mean preservative added was 242.6 milligrams. Also from this, we know that there were 60 random samples taken. And we also know that the standard deviation given in the question, which will always be population standard deviation, is 7.3 milligrams. So now we perform a z-test on our calculator. That is essentially the hypothesis testing. So in order to do this, you want to fire up your calculator and press on the Stat button. And after you've pressed on Stat, this is again calculate instructions for the TI-84, you want to go across with the menu up the top until it says Tests, which is the last one. So you press the right arrow a couple of times. Then you click on Z-test, which is the first one in the list, and you plug in the relevant data. Now the first one says, and hopefully you have the menu up in front of you so you can follow along with this, but the first one says Input, and it gives you two choices. Make sure that is set to Stat. After that, it's Stats. After that, you want to enter this value here, mu0. And mu0 is essentially the null hypothesis mean, the population mean that was claimed. And it was claimed that this machine would dispense 250 milligrams. So, 250 would be your mu0, your null hypothesis value. Now the next value, after that, and hopefully you're scrolling down and you're entering the values as we go along, but the standard deviation, we know from the question to be 7.3 milligrams. Now, it's very important here because you're probably thinking, hang on, hypothesis testing involves sample standard deviation. Well, yes, but your calculator wants to know sigma, population standard deviation, because eventually, later down the list, it'll ask for an n value. And the calculator's quite smart. It goes, okay, we don't want the population standard deviation when we're doing that z-score that we had before. We actually just want the standard deviation of the sample. And it will automatically go, okay, that divide by square root of n, and it will do it for you. So make sure you put it in, as said in the question, for the population standard deviation. So now, after that value's been entered, the next one down is x bar, which in this case is 242.6 milligrams. That's what they got from their samples. It's the sample mean, and then n is 60, because they tested 60 cans. Again, the units you don't actually put in, you don't type in mg or anything, so when you're putting it into the list it's like that. But again, it's important to get that idea of context when you're writing your final statement about what actually happened in your investigation, when you relate to the hypothesis that you originally had. And then after this, the last button is mu, and we leave it on the first one. And this one actually looks like this if I were to draw it out. So it goes mu and it has dot dot, and it's saying that it cannot equal mu naught. That's what we want to test. Again, I won't go into too much detail what the others do, however that's what you generally use just for this form of hypothesis testing that we're doing for the question. So once we've put that in, we get some values spat out when we go to calculate and press enter. It gives us a z value of negative 149. And if I just round it, I'll make it 0.4. Now let's think about what that means in context. It means that this value is 149.4 standard deviations to the left of the mean. Okay, that's very interesting. That's very interesting indeed. Just by thinking about that sheer fact, you can just sort of get a sense of where the sample mean fits on the distribution. And the likelihood that the sample mean would actually correlate to the population mean given in the claim that the machine is dispersing 250 milligrams. And of course, when you look at this, the calculator gives you a p-value of 0. Now, technically, if we had more advanced equipment, it would be able to give us an actual value for it. And I actually have worked this out on some more advanced equipment. And we get 4.13 times 10 to negative 15. So that p-value is really, really, really small. And of course, p is less than 0.05. A lot less than that value. An incredible amount less than that value. So the chance of that population mean actually being correct, and that the machine is dispersing the correct amount, we just got a batch of really dud samples, that likelihood is that. And that is a very, very small likelihood. So now from this, what we can conclude, based on technology, is of course that p is less than 0.05, hence the null hypothesis, denoted by H0, is rejected based on the evidence. Hence, in context, the machine needs fixing, as it is very unlikely to be dispersing a population mean of 250 milligrams. As you can see there, it's very, very unlikely. So from that, we've done a hypothesis test, and we saw that the claim isn't correct. The machine is not functioning correctly, and hence it needs to be recalibrated. Or it is very, 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 very likely that the machine is not functioning, so you probably want to calibrate it anyway. I mean, this is at the 0.05 significance level, but the value we got is, yes, it's quite low. In fact, the calculator even says it's 0, pretty much, because the probability is so, so tiny. So, it's very, very, it's very, very likely that the machine's busted. Okay, so if we were to work this out by hand, again, we'd just go through the same process and we'd get an answer. But in order to do it, we would have our values. We have X bar of 242.6 milligrams. We would have our mean, oops, I'll write mean first, mean of 250 milligrams, which is what the machine is meant to disperse as a population mean. And then we have N, sample size of 60 samples, and then we'd have sigma of 7.2 milligrams. So when we calculate this, what we would do is we would use our z-score formula, and of course we would use sample standard deviation, so it's x bar take mu on sigma over square root n. So in this case, it would be 242.6 take 250, divide by sigma, which is 7.2, on the square root of 60. And from that, of course, you can plug it into your calculator and you can check again. and we should get the same z-value. So if we were to do this, 242.6 on a calculator, take 250, and then that's over, and I'm using the fraction bars I generally use, 7.2 over square root 60. We get quite a significant z-score there as well. And it's because of that that we actually say, well, okay, the probability is incredibly low. And if you get anything above 1.96 as a magnitude of your z-score, then you can actually reject the null hypothesis at 0.05 significance. And that's what I'm going to go on to now in the next question. Generally, we'll be asked to calculate a p-value. Remember to see the first video on how to calculate a p-value. Again, it's just working out, okay, z-score, work out the proportion below, proportion above, and then you work out that probability using normal CDF, and then you multiply it by 2 to account for that, and then you have your p-value. Very simple. But this is a little trick if you don't need to calculate the p-value, and it can save you time. Okay, so I'm not sure if you're aware of this, because we haven't actually done a confidence intervals video as of yet, but if we look at 95% of the distribution here, and we have mean, it's normally distributed, this value here would be a z-score of negative 1.96. And the same would be on the other side, and 95% of values would fit in there. Of course, you may remember this based on the empirical rule, as 95.45% of values obviously fit within 2 standard deviations either side of mean. So now, based on this, we can actually say, well, okay, if it's 0.05 significance, and there's 2.5% that side, and there's 2.5% that side that are outside of that boundary, then if the z-score is greater than, in magnitude, if z is greater than 1.96 in magnitude, then of course it means that the null hypothesis is going to be rejected because the sample mean is going to be too far out, and it's going to be very unlikely that the population mean claim is actually correct. So the alternate hypothesis will be supported. So in order to do this, I'm not going to calculate a p-value in the next problem, but we're actually going to work through the process with an alternate hypothesis and a null hypothesis, and work out, well, okay, if the z-score is going to be greater in magnitude than that, we can immediately reject it, or we can immediately support it. So remember that 1.96 value. Comes in handy with this, and it comes in handy with doing confidence intervals, which we'll focus on in my next video. Okay, so now what we have is the following set of statistics, and again, it's in a contextual problem form. So the contextual problem says, quick shave produces disposable razor blades. They claim that the mean number of shaves before a blade has to be thrown away is 13. So that's mu, the population mean, and that's the mean they're claiming. A researcher wishes to test this claim and asks 30 men, well, we have a sample size, to supply data on how many shaves they got from one quick shave blade. The researcher found that the mean of the sample was 12.8. So x bar equals 12.8. Use this information to calculate the manufacturer's claim at a 5% level. Okay, so we're looking at a 0.05 significance level, which we generally look at anyway, if population standard deviation is 1.6. Of course, that's the last piece in the puzzle that we always need. So we're looking at number of shaves, these values here. Okay, so I'm going to get rid of the 0.05 significance level because that's generally inferred anyway, and let's use the z-score formula. So we have the sample mean, take the population mean, over population standard deviation divided by square root m, which of course gives us sample standard deviation. So now, let's derive. So z equals x bar, in this case, is going to be 12.8. Take mu, which is going to be 13. That's going to be on sigma, which is going to be 1.6. and that's going to be divided by the square root of 30, and hence our z value is going to be, and we can go to our calculator, and we can put it in, and we can derive from this. So we have 12.8 take 13, and then we have an alpha over another fraction bar, and then we go 1.6 divide by the square root of 30, and we can see that equals negative 0.685, and of course that is less than 1.96 if we were to take into the fact that, of course, it's less than 1.96 if we were to take into account that that is actually, if we were to just look at the magnitude rather than the actual negative there. And so, as a result of this, it means that our H0, which is a null hypothesis, is supported, because, of course, it's actually outside of that. If we were to draw it, we can see that one standard deviation to the left would be 34%, and we could see it probably, because the z-score's less than one standard deviation, it would lie in that standard deviation there, so we have x bar there, and because it's so close to mu, it's very, very likely that mu is the population is the population mean. HO is supported, hence the manufacturer's claims about the shaving equipment are supported. And, of course, it's possible that the population mean equals 13 shaves. So now on to one last section. So you've seen how we can actually just take a quick shortcut there, and we've seen how we can use the alternative and original hypothesis, alternate and null hypothesis on the calculator. Now what we need to do is calculate what sample size is large enough for the null hypothesis to be rejected, or for what values of the sample mean will it be rejected. So it says here, to test the hypothesis that H little naught 0, so the null hypothesis is where mu equals 40. So someone's made that claim, and the alternate hypothesis is that mu does not equal 40. But it asks here, for what values of x bar will a null hypothesis be rejected at the 0.05 significance level? So, of course, it means that it's going to have a z-score of less than negative 1.65, it's going to be out there, or greater than 1.96, why did I say 65? 1.96, and we have 2.5% there and 2.5% there. So that's what it's sort of asking. If you don't get that quite right away, then you will get it in a moment when we go through the question. But it says that they took a random sample size of 60. And it also says that the sample standard deviation is equal to 7. They actually write it as S, I'll write it as sigma. And they say that they want to calculate it so the null hypothesis will be rejected. And hence it needs to be an extreme outlier. Okay, so for this case, what we do is we take our standard z-score formula. However, we want our values to be less than or equal to negative 1.96, because of course that would put it in the null hypothesis being rejected, because it's too far away from the population mean for it to be reasonably, reasonably possible. It'd be unlikely. But from that we can say that, okay, we want to work out x bar, and we need to take the mu from it, and the mu, again, is going to be 40 in this case, because that's what the population mean was as a test. And then we have sigma as the next value over square root n, and it's very simple what we do next. We just have that statistic that we need to work with, and we also know that it will be rejected if it's going to be on the other side, and it's going to be greater than 1.6. So we set up the same thing. So in order to solve this, we can simply simplify the denominator there, and then rearrange to get x bar, and it will give us a region for x bar. So in order to do this, I'll go to my trusty calculator, and I will go 7 divided by square root 60, and it gives us a value of, and I'll rewrite this in here just to make it a little simpler, 0.903696, and I can write the same on there because of course it's the same value, so 0.903696, and then what I do is I bring this up to the other side from the denominator on the left hand side to the numerator on the right hand side, and we can multiply that together. So in this case I'll just work it out quickly beforehand, but negative 1.96 times by 0.903696, just double checking I got it right there, will give us a value of 1.7712. So it's negative 1.7712, and we got rid of the denominator on that side. And the same thing happens here, but of course it's going to be positive because a positive and a positive will always make a positive. So we get is greater than 1.7712. And then we simply bring the 40 to the other side, so this is going to go over there and it's going to be plus 40, and this is going to go over there and it's going to be plus 40, and then as a result x bar is going to be equal to negative 1.7712 take 40, plus 40, sorry, which can also be rewritten as 40 take 1.7712, and then on this side x bar is going to be equal to 40 plus 1.7712. And of course it's not going to be equal to, but we need to use inequality signs. Very important. And this is for the values to be rejected. So we simply go through this and do the arithmetic here. And for this side we get that x bar must be less than or equal to 38.23, sorry, when we round it. And on this side we get the x bar must be greater than or equal to 41.7712. And then from this we can say, okay, the null hypothesis will be rejected if it's outside these values. So as you can see, it's obviously got to be reasonably less than or reasonably greater than in order to get the values that will actually allow you to say, well, it's very unlikely for that population mean claim to be true. There is insufficient evidence to support it, or something along those lines. So make sure you know your terminology, make sure you know what you're talking about, and understand the basic skills of hypothesis testing. And that's all from me. Hopefully you enjoyed the video. If you have any questions, again, leave them below. But I reckon that that's pretty much everything I wanted to cover. So remember the process, and thank you very much for watching.